everybody. My name is Bryce, and I'll be talking about the Stirling engine. So some heat engines and thermodynamics background. The heat engine converts thermal energy into mechanical work by operating between a hot reservoir and a cold reservoir. The hot reservoir flows into the engine at a temperature TH and is converted into work, and the rest of the heat that is excess flows into the cold reservoir. And according to the first law of thermodynamics, the net work is equal to the Q input minus the Q loss, the heat loss. For the ideal Stirling cycle, it consists of 4 processes. The first one is isothermal expansion, where the working gas expands and receives heat from the hot reservoir. The next is constant volume cooling, where it flows the now expanded gas flows into the regenerator, where it releases heat into the regenerator and is stored for step 4 or process 4. Next, it goes through isothermal compression, where it is compressed and rejects heat into the cold reservoir. Finally, it goes through constant volume heating, where it flows back into the regenerator and absorbs all that heat that was previously released in constant volume cooling. The regenerator is a key part of the Stirling engine and is a reason why it is so efficient. The regenerator stores the heat from constant volume cooling during the cooling process, and then absorbs or returns the heat during constant volume heating. This reduces the external heat needed to perform or to produce work and improves the efficiency of the engine in the long run. So for the efficiency of the Stirling engine, an ideal Stirling engine with perfect regeneration, it has the same efficiency as the Carnot cycle, and it can be calculated using eta is equal to 1 minus cold temperature divided by the hot temperature. Real engines have lower efficiency due to various losses, such as heat transfer loss, friction, and imperfect regenerators. Typical real engines have about a 30 to 40% efficiency, and this can be slightly lower, or usually slightly lower than real diesel engines, and can be compared to, equal to, or slightly lower than, or higher than a real Rankine cycle. A Stirling engine has 3 configurations, or 3 main configurations of themselves. Type 1 is an alpha type, type 2 is beta, and type 3 is gamma. Alpha type has 2 pistons in separate cylinders, as you can see, and typically have higher power outputs than the others. Beta type has 1 piston and 1 displacer in the same cylinder, as again you can see. And then gamma type has a piston and displacer like the beta type, however they are in separate cylinders, as you can see again. Gamma types are more commonly used in demonstration models, as they are much easier to build than the others. Stirling engines have many or several applications. Some include solar power systems, heat recovery, waste heat recovery, submarine engines, and even space power systems that companies like NASA develop. So for solar power systems, the sunlight is concentrated into the heat pipe receiver with 2 mirrors. This then heats up the working gas in the engine, creating the hot reservoir. On the other side, the ambient air is cooling down that same working gas to create the cold reservoir, and the temperature difference between the 2 drives the engine, creating the cycle, producing work, and this work is converted into electricity using generators. The Stirling engine has many advantages and disadvantages. This includes quiet operation, high efficiency, high theoretical efficiency, and can run on many heat sources. However, they typically have slower startup speeds and require complex heat exchangers that increase the cost significantly and increase the engineering difficulty. Finally, some key takeaways. They are closed cycle heat engines that operate between hot and cold reservoirs. They contain 2 isothermal and 2 constant volume regeneration processes. And because of regeneration, the theoretical efficiency is high enough to approach Carnot efficiency. However, the real engines typically are around 30 to 40% at moderate values.